All right, everyone, welcome back to more calculus. Today we're going to be looking at one of the more meatier parts of the AP Calculus curriculum, and this is the volume of solids in a three-dimensional space. So we're going to do things pretty specific here in calculus, and this isn't going to cover every kind of three-dimensional shape that we can imagine, but it will cover a lot of the shapes that we could have imagined. I don't know if that works. But in any case, this is the meat and potatoes, one of the culminating, I guess, skills here on AP Calculus. So let's get to it. We're going to go with actually one of my favorite parts of Star Wars, which is The Empire Strikes Back, and we're looking at Han Solo kind of encased in what they say are frozen in carbonite, which I don't think anyone actually knew what that meant when they said it, but they just went with it. So what we're going to do is we're going to get something that kind of looks like that, and we're going to try and find the volume of it. Okay, so we're going to look at a method of area called cross sections. So we're going to start with this function right here, y equals 2 sine of x pi over 4, which I guess you can argue kind of looks like Han Solo in there. Not exactly, of course. And we're going to go from x equals 0 to 7. I imagine that's going to be in feet. And we're going to say that the cross sections, if we cut the cross sections of Han Solo here, if we just slice off a piece here, it would be kind of a rectangle. And it's probably the easiest one is to look at this one right in the bottom corner. Looking at this rectangle right here, all the slices are going to be kind of like that rectangle. They're going to have a length of, I think we said 5 feet, and the height of the rectangle is going to really depend on where it falls along this curve. So a rectangle over here will have a bigger height than a rectangle over here. Okay. And that's kind of what we're trying to show here. And obviously when we put all these rectangles together, they're going to kind of form something that is close to the shape of that plaque. So the prisms, these are all prisms because they are a three-dimensional shape and the sides are all rectangles. And these are rectangular prisms because what I'm calling the face, just the front part here, these are all rectangles. So how do we compute the area of a rectangle? Well, before we do that, let's see what we have here. Considering the volume of one typical cross-section, the width of the cross-section is a distance from the curve to the x-axis. So we're calling this distance from here to here, we'll call that the width. Although in terms of Han Solo, I think that's actually the height. And then this distance from here to here, we're saying that that's going to be equal to 5. And we're calling that the length. And then the width of this, we're going to call that the depth. And that's the delta x. That width is kind of variable. It really depends on how skinny do we want to make all of these cross sections. So we'll just leave that as a delta x. That delta x should be triggering some memories for you right now. So the volume of this cross section is going to be the same thing as the volume of a rectangular prism. Or any prism, the volume is the area of the face multiplied by the depth of the prism. In our case, we have the face area is a rectangle. So the area of a rectangle is length times width. Part of what makes this section difficult for students is this area formula is different for every problem that you do. Sometimes you'll get a rectangle, sometimes you get a triangle, sometimes you get a circle, sometimes you get a semicircle. It really just depends. So we're going to plug in the stuff that we know. The length, of course, we knew that that was 5. I think I put that in the wrong place. The width, we're saying that that's 2 plus sine x pi over 4. And then the depth is that delta x. So in essence, this formula right here, that's the volume of one slice, length times width times depth. Now, if we put it all together and we stack up all of these and add them all together, then what we would say is that the volume is about equal to all the areas multiplied by all their depths just added together. So that gives us this formula right here, where volume is a summation, an addition of 5 times a quantity of 2 plus sine pi x over 4 multiplied by delta x. So we're adding together a bunch of, in essence, volume formulas. But as we're going to see, we can't, because they are prisms, we can think of it as an area formula multiplied by a delta x. Once you've made your peace with that, made your peace with the fact that we have an area multiplied by delta x, it's pretty easy to see where we're going here, because we're going to let each of those delta x's basically go to 0, which is what we see here. Make all the delta x's go to 0, and that will turn the summation into an integral. And if you think about what we did, we basically found an integral here, which is area formula multiplied by dx. So if I need to find the area, the volume of something, I just take the cross-section area and I multiply by dx and I integrate the entire thing. Most of the time we're going to say that you just need to integrate the area formula. And that's the key here. The volume is an integral of the area formula dx, where that dx is the width of each of the cross sections. Now we probably should figure out the volume of the shape that we were just talking about. So let's do this really quickly with the calculator. Okay, and we're going to put that area formula right here. Or that's the length, that's the height, I'm sorry, that's the height formula. And we're going to integrate that. So we'll go to the home screen. We'll go ahead and do Math 9. And we're going to integrate from 0 to 7. 5 times y1 multiplied by dx. Now, if I look at this one more time, this 5 is the length. This y1 is the height. And the dx is the width. So length times width times height. That's the volume formula. Let's integrate. 73.729. So that's the volume approximately of that integral that we set up, which was supposed to be kind of like the Han Solo frozen in carbonite. In any case, when it comes to calculus, there are 4 things that you need to do here. And the first one here is you want to calculate the coordinates of every corner on the base of the solid. So we're looking at the base of the solid and then things being built on top of the solid. So we got to kind of differentiate between those 2 things. So find the coordinate of every corner on the base of the solid. You're going to use that to find x min and x max. Next, you need to find an equation for L, which would be the length of the base. Usually, the length of the base is going to be an f of x minus a g of x. All of the area formulas that we do will be based on that L, the length. Next, find the area formula of the cross-sectional face. That area formula will be in terms of L. And then after we can figure out that area formula in terms of L, then it's just a real quick substitution to turn that into an area formula in terms of X. You need to lean into your knowledge of geometry here because, I'm not here to teach you all the geometric formulas for an isosceles triangle or a right triangle or anything like that. And nothing in calculus should be, or at least academically, nothing in this class should be some esoteric volume formula. So if an equilateral triangle is an esoteric volume formula to you, then you need to brush up on your geometry, okay? Next, you're going to integrate the area formula. For cross sections perpendicular to the x-axis, A will be the smallest value of x from step 1, and B will be the largest value of x in step 1. And the integrand is just going to be whatever you came up with in step 3. Differential is going to be dx. So that's a lot of things to go over. If you do this enough, it becomes pretty routine, but it takes practice, and that's the key here. You need to practice this. Not once, not twice, not 5 times. You need to do this a lot. So let's take a look at this problem. We want to find the volume of a solid bound by the coordinate axes and the line x equals 4 minus 1/2 x, and the cross sections perpendicular to the x-axis are equilateral triangles. So equilateral triangles, we're going to have to start thinking about that area formula. So first off, what are the corners of this base? Okay, this is 0, 0 over here. This is 0, 4. And this over here is 8, 0. So I can already tell you the smallest value of x from those corners is 0, so A is 0. And the biggest value of x in those is 8, so B is equal to 8. That's for our integrand. Next step, the length. So the cross sections are going to be perpendicular to the x-axis. So you want to draw a line perpendicular to the x-axis from the curve to the bottom curve, from the top curve to the bottom curve. And L is going to be however long this line is. Okay, so this line is not in any particular place, so it needs to be a function of x. So right here, any y coordinate here is going to be equal to 4 minus 1/2 x. Again, that should be a function. Now, the y coordinate down at the bottom here, that's always going to be 0. So that's why we have the 0 here. So that tells me that L is going to be 4 minus 1/2 x, period. Now, area formula. From geometry, we know that the area of an equilateral triangle with a side L, notice that L is always the bottom here. If this side is L, then the area of an equilateral triangle is root 3 over 4 multiplied by L squared. Again, I don't have time in calculus to go over all of these these area formulas for you. So you're going to have to really review your geometry here. So if the area is root 3 over 4 L squared, then in terms of x, we're just going to substitute L right here. It's root 3 over 4 multiplied by 4 minus 1/2 x squared, because that's L squared right there. Next, we're going to go ahead and integrate. So we've got volume equals integral from A to B, and A was 0 and B was 8. Let's scroll a little bit. And then the area formula was root 3 over 4 multiplied by the quantity 4 minus 1/2 x whole thing squared. Now, sometimes you'll get a calculator, sometimes you won't get a calculator. It really just kind of depends. So if I want to integrate this, it looks like, well, first of all, it looks like I can take that root 3 over 4, take that out of the integral. 4 minus 1/2 x squared dx. Oop, squaring the wrong thing here. And the way I'm going to choose to do this, and you can do your integral any way you like as long as it's correct, I'm going to say u is equal to 4 minus 1/2 x. That makes my du equal to negative 1/2 dx, or my dx equal to negative 2 du. And I'm going to use a total substitution. So when x equals 8, u is going to be equal to 4 minus 1/2 of 8, which is 0. Yeah, 4 minus half of 8 is 0. And then u of 0 is going to be 4 minus 1/2 of 0, which is 4. So in terms of total substitution, this is going to be root 3 over 4. The lower limit is going to turn into a 4. The upper limit is going to turn into a 0. The integrand is going to become u squared, and the dx is going to become negative 2 du. Now we're going to do a couple of things here to make my life easier on the integral side. And the first thing is to factor out that negative 2. And that turns into negative root 3 over 2. 2 times root 3 over 4 is root 3 over 2. And that's going to go from 4 to 0 of u squared du. Now the other thing that I can do is, since I have the negative here, I can actually reverse the limits of integration from 0 to 4 at the cost of another negative sign, which basically just kind of rights the ship. So that looks pretty good, not bad. Since I've already gone to u, and I've made a total substitution, there's no reason for me to go back to my x's. I'm just going to keep it in terms of u. So this is going to be equal to root 3 over 2 multiplied by 1/3 u cubed, and we're going to go from 0 to 4. Okay, 4 cubed is 64. 64 divided by 2, actually let's slow down. Root 3 over 2 multiplied by 1/3 times 64 minus root 3 over 2 times 1/3 multiplied by 0. Okay, and then we're going to do some simplification, of course. 64 divided by 2 is 32. So this is going to be 32 root 3 over 3 for the volume. So that's what we need to do. Most of that integration stuff should be review. But this right here, this is a formula you need to really work with, okay? So let's get to our, the next page here, which would be important ideas. What are the important ideas? Well, the important ideas are, for every volume, every problem, and I really mean this, every problem that we do involving volume in this section 8.3 is going to be the same formula. Okay, same formula. Learn it now and use it forever. The volume is the integral of the area formula dx. There are 4 things you need to solve for. You need to figure out the corners. You need to figure out the length from the top curve to the bottom curve. You need to find the area formula, and then you integrate. 4 steps. Clay? I don't know. Volume by slicing. Most likely, the geometric formula is going to involve the distance from the top curve to the bottom curve. Actually, that's kind of true for everything. And the area is just whatever that function is of L. So, let's see if we can figure this out. Jabba the Hutt wants a new carbonite. He decided on a tuk-ata to be frozen in a particular shape. The carbonite block will have a base region bound by the curves f of x equals 1/8 x squared plus minus 2x plus 8, and g of x equals as you see. The cross sections of the solid perpendicular to the x-axis are semicircles with diameters that reach from f of x to g of x. So what is the volume of this carbonite block? Now, I got to tell you, this isn't a really easy problem. Definitely not a softball problem. This is a good one. First thing we should probably do is graph the base. Now, you're not expected, in this section, there shouldn't be anything too difficult to graph. And if there is something that is more than a little bit, you're going to be using a calculator here. So I'm going to go ahead and graph this using my calculator. First thing to do is to get those functions into the y equals menu. And then since I have no idea where these graphs are going to intersect, I'm just going to use Zoom Standard just as a starting place. So let's see what we got. Okay, there's f of x, and we should be getting g of x over here. Okay, so it looks like I'm only going to be in the first quadrant. It also looks like I need to extend this to x equals at least 15, if not 20. So let's modify our window. If I want to be in the first quadrant, my x minimum should be somewhere close to 0. I like making it 0.5. And our x max, let's make it 15 for now. Y min, again, I'm in the first quadrant, so I'm going to make that negative 0.5. And that y max of 10 looked okay to me. So now I'm going to push graph and see what we got. Here is f of x. And here is g of x. Let's see, did I go out enough? Yeah, I think so. So that looks pretty good. Let's put that into our work. Now remember, this is just the base of the region. We're going to be building semicircles on top of this, much like we did rectangles on the previous region that we just did, or isosceles triangles on the one that we really just did. Let's get back to our shape here, and I'm going to need to know what are these points of intersection. So I'm going to second calculate and intersection. We did this earlier, so I think I'm on the first curve, yes. I'm on the second curve, yes. And I'm going to guess this looks like it's right around 1. So I'm going to just type a 1 in here, push enter, and that's going to give me that first intersection point, 1.23166. On my paper, I'm going to label this at x equals a, and I'm going to write a equals 1.23166. So I'll never have to write that number again. And we'll do something, before we do that, let's go back to our calculator, and I'm going to quit. And right now, if I type x, that's going to give me that same number, and I don't want to lose that. So what I'm going to do is I'm going to take that number, and I'm going to store it as a. Okay, so now when I want this number on my calculator, I can just use the letter a. We're going to do the same thing for letter b. We're going to find an intersection. Second, calculate. Intersection is 5. Are we on the first curve? Yes. Are we on the second curve? Yes. And what does that look like? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That looks like right around 13. So I'll make my guess 13 by typing the number 13. And I got 12.99058. Same drill. Label the diagram. Make B, write down B equals 12.99055. Go back to the calculator and we'll make that x, whatever is currently in x, we'll take that and we'll store that as b. And so on my calculator, all I need to do type is a and b if I want to use those values. Next. Here on my graph, I'm going to draw from the top curve to the bottom curve, and this is my value of L, or this is L, the distance from the top curve to the bottom curve. And the top curve is the red curve, which was g of x. And the bottom curve is the blue one, which was f of x. So L is equal to g of x minus f of x. And I don't need to write them because they are already in my question. So anytime I mean g of x, I am going to mean this formula over here. This is the g of x formula, and this right here is the f of x formula. Now, next we have cross-sections are semicircles. Semicircles. So let's draw a semicircle. And first of all, this is L right here. And we're going to draw a semicircle on top of L. Here's a semicircle. Now, in terms of L, the area of a semicircle is equal to 1/2 pi r squared. L happens to be the diameter here. So I have to do L over 2 if I want the radius. So area is equal to 1/2 of L over 2 squared. Okay. Now, don't make yourself liable for any algebra fail here. 1/2 squared, this is 1/4 times 1/2, that's 1/8. L is g of x minus f of x squared. So that's my area formula. So what have we done? We found the corners. We found L, the length. We did the area. And so the last thing is to integrate. So the volume is going to be the integral from a to b of the area formula dx. Same formula for every volume that we do in section 8.3. Now, I know what A is. A is, well, I already wrote it down. It's up here. Same thing with B. B is up here. Now, the area formula is 1/8 of g of x minus f of x squared, and of course, dx. So let's go ahead and chuck all that in the calculator and see what we come up with. We're going to integrate. And then we'll put A down there and put B over here. I don't want to waste time typing out that number and then checking it 5 times because I'm not sure I did it correctly. And I need a 1/8. Okay, f of x, or g of x minus f of x. G of x I put in y2. F of x I put in y1. And we'll square that dx. Let's see what we get. All right, 47.422. The volume of the Tuch-Ata carbonate is 47.422 cubic units. So, I hope you can see that these 4 steps here really are going to take you through here. And you got to think about all 4 of those as we compute our volumes, okay? And one more time, so important, the volume is just the area of or the volume is just the integral of an area formula. So that's our first step, our first look at volume formulas in Calculus section 8.3. We'll be definitely doing more, and I will see you for that next time.